Good morning, everybody. Today we will continue with direct current circuits. So what we have seen up to that part of our lecture, we have seen that, or we have assumed that all the EMFs and resistance are constant. So they are not changing by time. So we have considered that potentials, currents, and powers are independent of time. But if we have such circuit, including capacitors, then we have to consider the currents, voltages, and powers do change with time. So today we will concentrate on this. Actually, many devices incorporate circuits in which a capacitor is alternately charged and discharged, like this one. For example, this is one of the very common example. Automobile turn signals contains this type of circuits, including capacitors, and also flashing traffic lights and electronic flash units, which we have discussed during chapter 24. All they contain capacitors, and they are example of such circuits. So now today we will talk about how to charge and discharge this capacitor. Here we have EMF, and here we have a resistor. Here we have a switch. We can open and close that switch. So by using EMF, we will charge that capacitor, and after removing EMF, we will try to discharge it, and we will learn how the charging and discharging mechanism within that circuit. So let's continue with charging a capacitor. A circuit such as this, like this one, has a resistor and a capacitor in series, is called an RC circuit. Here we have R resistor, here we have a capacitor, so they are connected in series. Then we call such circuits as RC circuits, okay? So here we have a battery. Let's consider that this is an ideal battery. It has constant EMF and zero internal resistance. And we can also consider that the resistance of that wires, resistance of that wire, resistance of that wire are zero. We ignore the resistance of all the connecting conductors. Then we start with the capacitor initially uncharged. At the beginning, we have an empty capacitor, and the total charge on the capacitor is zero. And the switch is open, okay? So there is no current on the circuit. So current is also zero at the beginning. So now let's consider that we have closed the switch, and then current started to travel within that circuit, okay? So at some initial time when t is zero, we close the switch, completing this circuit and permitting current around the loop to begin charging the capacitor. So what do you see here? As the time increases, the charge on the capacitor, Q charge on the capacitor, will increase while the current decreases in the circuit. So you can understand why the charge, you can understand that the charge on the capacitor increases, but why the current decreases. So this part is very important. I will shortly explain, and then I will show you the details of that mechanism. So when we close the switch, this was initially zero, this situation, and then we close the switch. So from positive to negative, we may expect a current in the circuit, right? So what is the current movement of positive charges from positive to negative, right? We have seen already in previous chapters. So positive Q charges will be collected on that panel of the capacitor, and negative Q charges, same amount of negative Q charges, will be collected on that side of the capacitor, right? So by time, the amount of that Q will increase, and these charges will repel other incoming charges. Okay, so Q charges would like to come to that side of the capacitor, but since we have many Q charges here by time, they will repel them. Okay, and the same mechanism, negative Q charges are coming here, so they are also repelled by these negative charges here. So by time, this current will decrease. This current will decrease. Okay. So by time, the charge on the capacitor increases and current decreases. Don't forget this. We will go into detail. So here we have charge on the capacitor. Okay, final charge of the capacitor. It depends on the, this is the charge at certain time on the capacitor, and this is the final charge on the capacitor. Final charge is shown by Q final, okay? It is equal to 1 minus E over T over RC. This R is the resistance of the resistor, this C is the capacitance, and here we have T, which is time. So what is the time dependence of the Q, charge on the Q? Let's have a look. This R is constant. This capacitance is also constant. Final charge on the capacitor is also constant. So only changeable parameter here is time. If you increase the time, this parameter on the right side will go down, will go to 0, and then Q will be equal to Q final after certain time. Here you can see behavior of Q as a function of time. This is the time scale. This is the charge scale, Q scale. This is the maximum charge on the capacitor, Q final, okay? And it goes to maximum charge value on the capacitor exponentially with time, okay? So this is the time versus charge on the capacitor during charging. So then what about the current? We have also seen that when the charge is increased here, the current will be decreased, okay? So what is the time dependence of the current? Here we don't have any more constant current, we have a decreasing current. So how to get the current? If I take the time derivative of the charge, I can get the current. So here we have the current, which also depends on the time. This is the initial current when the time is 0. Okay, let's consider that when the time is 0, we have closed the switch, and the total current here at the beginning is flowing in the circuit, which is given by I0 initial current, which is equal to EMF over R. We will calculate all the things. And the current depends on time. This is constant, initial current constant, because EMF is constant, resistance of the resistor is constant, capacitance is constant. So only changeable parameter here is time. So if we increase the time, then this term will go down. So then the current will decrease. So here we have a graph of that expression. This is the time scale from 0 to certain second or certain time. And this is the current scale. What we have here at the beginning, the current is given by I0, and it decreases by time. The current decreases exponentially with time as the capacitor charges. So, do you have any question in that part? Then I will go into detail how to calculate that Q time-dependent Q and how to calculate time-dependent current. Any question here in that part? Okay, now derivation of general expressions for charge and current as functions of time. We will get this expression, we will also get this expression. So let's consider that. Maybe first of all, I should tell you that here, for example, instead of capital I use small I. Instead of capital Q, I have used small q. Can you see that? So if the voltage, current, and charges on the circuit do not change, we use capital letters. This is preferred in the book of Young and Freedman, okay? But whenever the voltage, current, and Q depend on time, so they are changing by time, we use lowercase letters, okay? So then we can understand that voltage, current, and Q is time dependent, okay? So here we will also use that symbol if they are changing by time. So here we have three conditions. One, this is the first one, second one, and third one. Three conditions. So the first condition, when time is 0 at the beginning, you just close the switch and you allow the current to flow within the circuit, okay? So the capacitor is uncharged at the beginning when the time is 0. Total charge on the capacitor is 0. And the voltage difference between B and C is also 0, because voltage difference between B and C is given by charge over capacitance of capacitor. We have seen this one during the chapter 24. So since the charge at the beginning is 0, the potential difference between B and C will be 0. Okay, then we have it here. Then for that condition, if we apply Kirchhoff's loop law at time is 0, what we have here, just choose the direction of the current like this from positive to negative, and just choose a loop like this. This is the travel direction. We have learned all these things during the last lecture. And since the travel direction from negative to positive for the EMF, we have positive here. And here, this is the current direction. This is the travel direction. And since the current direction and travel direction are same, then we have negative contribution from that resistor minus this is the initial current in the circuit when the time is 0, and the resistance of the resistor, they are equal to 0 according to Kirchhoff's loop law. Then take this one on the right side and take current from that expression. Finally, we can get current, which is initial current when the time is 0. You just close the switch and the current is started. So this initial current is given by EMF over R, or potential difference between A and B, VAB over R. Okay, this is the initial current. So let's continue. So as the capacitor charges, so this was when the time is 0. Now, second condition, we continue to charge the capacitor. Time is increasing. Okay, so what happens here? By time, the charge here on the capacitor will increase. Since the charge increases, the potential difference B and C will increase. So VBC increases. And by time, current here will decrease. Since current decreases, VAB, potential difference between A and B, will decrease, okay? Because current is decreasing. So the sum of two voltages is constant, and equal to EMF. So voltage here, VAB, between A and B, and the voltage here between B and C, voltage BC, they are, the sum of them equal to EMF. Okay, this is the produced voltage, the voltage dissipated here and used to charge the capacitor. Okay, so VAB plus VBC here will give us the EMF of the circuit. But what we are seeing here, by time, this VBC potential difference here increases. Since this is constant, this should decrease. Indeed, this is decreasing because current decreases. Okay, so after a long time, you have waited for a long time, then the capacitor is fully charged. And when the capacitor is fully charged, the current goes to zero. Okay, there will be no current in the circuit if the capacitor is fully charged. And VAB decreases to zero. So the VBC will be equal to the EMF since this is zero when the capacitor is fully charged. Okay, so at the intermediate case, capacitor has certain charge, but it is not fully charged. So intermediate case, let's have a look. Just try to apply Kirchhoff's loop rule at some time t after the switch has been closed. So apply Kirchhoff's rule. Just choose the current direction like this, from positive to negative, and just choose travel direction in the same direction with the current. Then we can find positive epsilon because the travel direction is choosing from negative to positive for the EMF. Then here we have current direction and travel direction are same. Then we have negative for the resistor, minus I times R. And for the capacitor, the travel direction from positive to negative. Like EMFs, we will also take negative in that case. So what is the potential difference here? Q over C. And if I take current from that expression, finally I can get current like this: EMF over R minus Q over RC. Okay, so what you see here, EMF constant, resistance of the resistor is constant, capacitance is constant, R is constant. So, but Q is not constant. Q changes by time. Q was zero at the beginning and then it increases and it reaches its maximum value, right? So Q is not constant. Then this current here in the circuit also is not constant. So let's consider that we are charging the capacitor. You increase the charge, you increase the charge, you increase the charge, and this term given by negative number, okay, which is increasing, 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 and it becomes equal to that one. This second term becomes equal to that one. Then the current becomes zero when the capacitor is fully charged. So then current becomes zero. When the current is zero, put zero here, EMF over R minus will be equal to Q over RC. Current is zero. So what is Q here? When the current is zero, it has final charge of the capacitor. We have fully charged the capacitor and the current went to zero. So by using that expression, we can get final charge, which is given by capacitance times EMF. Capacitance times EMF gives us the final charge of the capacitor here. So from that expression, we can understand that the current is not constant, changes by time as the charge on the capacitor changes by time. So how to get expression for this charge as a function of time, and how to get expression for this current as a function of time. Now let's do that. Take this expression, and we know that the current is given by time derivative of the charge on the capacitor, right? dq over dt, we already know this one. So take this one here instead of current, then we have that expression here, okay? I just put dq over dt here. So if I take 1 over RC and rearrange that expression here, I can write like this: 1 over RC times C EMF, C times EMF minus Q here. And I can also rearrange this one, okay? So I take this minus out, then here Q is positive and this one is negative, but here I put another negative, okay? So negative sign. So just same, I have just rearranged, okay? So here what we have dq, here we have q, and here we have dt. Take this one here and take this one here, then finally we get that expression dq over q minus c times E EMF is equal to minus dt over RC, okay? So what do you see here? If you solve that integral, so here we have q. What is q? What is the limit of that integral? Q starts from 0 and goes to q final. And what is the time? Starts from 0, goes to some certain time, okay? If you solve that integral, then q is given by that expression. C times EMF, and which is multiplied by that expression within the bracket, okay? Let me delete it. Okay, so what do you see here? This is Q, this is capacitance constant, EMF constant. Here we have resistance constant. Here we have capacitance constant. So all these parameters are constant within that expression. So the only changeable parameter here is time, okay? Look at this one. This is E over minus certain number. If you increase the time, this term will decrease. If you further increase the time, this term will further decrease. And finally, it will go to 0. Okay? So what do you see here? If this term goes to 0, this one will reach its maximum value. Okay? So at the beginning, this is a 0. When the time is 0, this term is 1. 1 minus 1, Q is 0. Then we have uncharged capacitor. Whenever we increase the time, this term decreases and this term increases, and then we increase the charge of the capacitor. So this capacitance times EMF here can also be written like this: QF. Here, what we have, C times EMF gives us the final capacitor charge. So if you take time derivative of this charge here, then you can get current. Just take time derivative of this guy or time derivative of this guy, then we will get that expression: E over R times E over minus times time over RC. So what do you see here? Time increases and current decreases. So we have get expressions for the behavior of current as a function of time and the behavior of charge as a function of time. Do you have any question in that part? Okay, so let's continue. What is RC here. Here we have RC. Here we have RC. R is constant, C is constant, so you may expect that this is also constant, right? It is called as time constant. Unit is second, okay, because it's time, so you can calculate it. So here we have RC, this is time constant. The RC is a measure of how quickly the capacitor charges and denoted by tau. Tau gives us RC. So when the tau is small, the capacitor charges quickly. When it is larger, the charging takes more time. So just put this RC here, tau here, okay? If it is bigger, okay, then it will take so much time to fully charge the capacitor. If this is smaller, then it will take less time to fully charge the capacitor. So since it depends on the resistor, if we have small resistance, then it is easier for current to flow and the capacitor charges more quickly. So if you decrease the resistance, then this will decrease, and here we have small tau, okay? As we have explained, the capacitor charges quickly. So R is given in ohms and C is given in farads, we have seen in chapter 24, and tau is given by second as a unit in SI system. So now let's continue with discharging a capacitor. First of all, we have charged the capacitor. It is fully charged. Now the charge is given by Q0 or Q final, okay? So before the switch is closed, the capacitor charge is Q0 and the current is 0. So that situation, we have charged the capacitor, okay, and capacitor is charged and current went to 0, and then we remove the EMF and open the switch, okay? So like this, capacitor is fully charged, current is 0 in this system because the switch is open. And now let's close the switch. What do you expect? There will be a current in the circuit. So what about the direction of the current? Let's assume that you don't know the direction of the current, okay? But we can find it. At some initial time, when the time is 0, we close the switch. And now we have a closed circuit, allowing the capacitor to discharge through the resistor. So the capacitor will be discharged through the resistor. As T increases, the magnitude of the current decreases. Again, the current is decreasing. In both cases, during the charging a capacitor, during a discharging a capacitor, current decreases. We have explained why the current decreases in case of charging. Here you can also understand you are losing the charges on the capacitor. So then the decrease in the current is logic, okay? The magnitude of the current decreases while the charge on the capacitor also decreases here, okay? So we lose charges on the capacitor and the current on the circuit also decreases. So now let's have a look. Charge on the capacitor, how it changes by time, and the current in the circuit, how it changes by time. So here we have the expression. We will calculate also that expression for discharging case. This charge as a function of time is given with that expression. This is the Q0, initial charge of the capacitor when it is fully charged, okay? So this, when the time is 0, the total charge of the capacitor is given by Q0. And here we have E over minus T over RC. This is constant, so this is constant. Only time is changing here. If you increase the time, then this term will decrease and Q will decrease. Here we have the graph of that expression. This is the time axis. This is the charge axis. At the beginning, when the switch is open, okay, the charge is given by initial charge or final charge of the capacitor Q is 0, then whenever we close the switch, current starts to flow within the circuit, then charge decreases by time with that expression. And look at the current here. If you take the time derivative of that expression here, you will get this formula, dq over dt minus q0 over rc. Just take the derivative of that function here, times e over minus t over rc. So what we have here, we have initial capacitor charge, resistance of the resistor, capacitance of the capacitor, and again, same here. So this is constant, constant, constant. Only time is changing. So since if we increase the time, then this term will decrease and then current will decrease. But what you see here, the sign of the current is negative. Why? Because for a discharging capacitor, the direction of the current is opposite compared to the charging case, from positive to negative, okay? During discharging. You remember during the charging, it was like this, from positive to negative of the EMF, okay? And this is the current direction. But now the direction of the current is from positive to negative, so opposite to the charging case. For this reason here, we have a negative sign. You can take, this is also constant, okay? Another constant here, minus Q0 over RC. And you can consider that this is the initial current at the beginning when the capacitor is fully charged and the system is open. So this current decreases by time with that expression. So you can see here that current has some certain number here, I0, and it goes to 0 by time. We have started from the negative because the current in that case is opposite to the initial case. Do you have any question in that point? Okay, let me calculate that current and that Q for the discharging case. Now suppose that after the capacitor has acquired a charge Q0, fully charged, we remove the battery from the RC circuit, and here we have an open switch. Then close the switch. When the time is 0, Q on the capacitor is Q0. The capacitor then discharges through the resistor, and its charge eventually decreases to 0. So this charge here will go to 0, okay? And the current on the resistor will also go to 0. If we choose the positive direction for the current, as in the charging case, okay, let's consider that you don't know the direction of the current, and again, you choose the direction of the current like in charging case. So let's choose that this is the direction of the current. Again, this is the travel direction of the loop, okay? So what we have here, travel direction, current direction, they are in the same direction. Then for the resistor, we can apply Kirchhoff's loop rule. Here we have minus I times R. And for this one, travel direction from positive to negative, then it is negative Q over C, which is equal to 0. And if we take the current from that expression, we can find minus Q over RC. This is the current in the circuit. Here we have found this expression. This is the current, this is the charge on the capacitor, and this is the time constant RC, resistance of the resistor times the capacitance of the capacitor. So what we are knowing that after a certain time, the charge on the capacitor decreases. So since it decreases, current also decreases. So here we have a negative sign. What is the meaning of the negative sign? Negative sign indicates that the direction of the current opposite to the initial current during the charging. So now we know that the current is given by dq over dt, and put this one here, then dq over dt is equal to minus q over RC here. So if you take this Q here, take this dt here, then we will get that expression. If you solve that integral, and if you solve that integral, you can get that expression. So talk about the integral limits. The charge will start from Q0, initial charge of the capacitor when it is fully charged. This is the lower limit, Q0, and upper limit is 0, because charge will go to 0 after a certain time. And the time here, the limits of that integral on the right side from 0 to t, okay? If you solve that integral, then the Q here will be equal to Q0 times E over minus T over RC. Again, time constant. This is a constant R resistance capacitance, and this is the Q0 initial capacitor charge. So what we see here, only the time is variable parameter here. So if the time increases, charge decreases. So the charge of the capacitor decreases by time. And what about the current? If you take the time derivative of the charge, we can get the current like this one. Take the time derivative of that expression, then we will get this minus will come here, Q0 over RC times, and this exponential expression again will be there. Okay, so what do you see here? This is constant, constant, constant. Again, only changeable parameter here is time. If you increase the time, this term will go down, this decreases, and thus the current in the circuit decreases by time. So we can call that this is the initial current minus Q0 over RC, initial current, and this is the time, this is RC. So if time increases, current decreases. Then we can explain the behavior of charge on the capacitor decreases by time during discharging a capacitor, and the current starts from negative certain maximum value, and it goes to 0 by time since the current decreases in the circuit, and the direction of the current is opposite to the during charging capacitor. So now let's talk about power and energy in RC circuits. So during the charging, we have EMF, we have resistance and capacitor here. If you apply Kirchhoff's loop rule, we have already got that that equation. This is the EMF. This is the direction of the current, direction of the travel. If you choose in EMF from negative to positive, then this is positive. Here, the direction of the current and direction of the loop are same. Then here we have negative, and from the within the capacitor, from the direction of the travel from positive to negative, then here we have negative Q over C, which is equal to 0. We have already done it. So take this EMF and put them on the right side, then we will get that expression, okay? So if you multiply that expression with current, multiply this side with current and multiply this side with current, and then we will get that one, I times EMF is equal to I squared times R for this one, and plus I times Q over C. So what do you see here? I times EMF. It is like PV, okay? I square R, we have learned all the things. This is power, this is power, this is also power. So this is the power supplied by the battery, okay? And this power, some part of this power is dissipated within the resistor, and some part of the power is stored in the capacitor, okay? So what about the energy? The total energy supplied by the battery during charging of the capacitor equals the battery EMF multiplied by the total charge. So the total energy supplied by the battery to that circuit is given by EMF times final charge of the capacitor. Then we know that from chapter 24, the total energy stored in the capacitor is given by QE over 2, okay? So 1/2 Q times E, we have already done it in chapter 24, you know that expression. So Q times E is produced on the EMF, and this one, half of it, stored in the capacitance. So then of the energy supplied by the battery, this energy, exactly half is stored in the capacitor and the other half is dissipated in the resistor. You can get this result by taking the integral over time of each the power quantities in equation given here. If you take the time derivative of this expression, you can get same result. So do you have any question in that part? Then let me continue with examples. So this is the example 26.12, charging a capacitor. Here we have a circuit. A 10 mega ohm resistor is connected in series with 1 microfarad capacitor and the battery with EMF 12 volt. Before the switch is closed at time t is equal to 0, the capacitor is uncharged. So at the beginning, this switch is open and the net charge on the capacitor is 0. The capacitance is uncharged. So what is the time constant? Time constant is this one, R times C, which is asked what fraction of the final charge is on the capacitor when the time is 46 seconds. And last question, what fraction of the initial current is still flowing when the time is 46 seconds? So you need these two equations for the charging case. We have already calculated them. So Q is given by that expression, I current is given by that expression. Keep this ones in your mind. Okay, so what was the first question? What is the time constant? Time constant is given by R times C. Resistance times capacitance. Resistance is given 10 mega ohm. Instead of 10 mega ohm, use ohm, 10 times 10 to 6 ohm. Instead of capacitance, we have 1 microfarad. Instead of microfarad, just use farad, okay? 1 times 10 to minus 6 farad. Then we will get 10 seconds, okay? So this is the time constant. So what is the second question? What fraction of the final charge is on the capacitor at time is 46 seconds? So charge at certain time is given by that expression, Q final times this expression within the bracket. So if you take the fraction of the final charge, Q over QF, take this QF here, Q over QF will be equal to that expression, 1 minus E over T minus T over RC. So T is known, 46 seconds, put it there. RC, we have already calculated 10 seconds. Seconds cancel each other. Then Q over QF is 0.99. So what is the meaning of that? After 46 seconds, the capacitor is 99% charged, okay? So what is the, so you can imagine that how this capacitor is charged, okay, within a very short time. It is very fast. So what fraction of the initial current is still flowing? So what is the current in that time? You can think like this. So at the beginning, the current is 0, charge is 0. Whenever you close the circuit, then initial current will start to charge the capacitor, okay? So this is the initial current. What fraction of the initial current is still flowing? Then take this initial current here. I over I0 will be equal to that expression. Then we know this RC and time is given, okay? Then we know the fraction of the initial current when the time is 46 seconds. So what is the meaning of that? the charging current has decreased to 1% of its initial value. So at the beginning, we have I0. So when you close the switch, so current will be here in the circuit, and this initial current is I0. And after 46 seconds, the current, this initial current, will drop to 1% of the initial one. So this is the charging a capacitor. Do you have any question in that part? Okay, let me continue with discharging a capacitor. The resistor and capacitance of that example are reconnected as shown like this one. Okay, we remove the battery and we open the switch. The capacitor has initial charge of 5 microcoulomb at the beginning and is discharged by closing the switch at time is 0. Just close the switch and then current will pass through on the circuit, and then capacitor will be discharged and current will decrease. At what time will the charge be 0.5 microcoulomb? At the beginning, charge here is 5 microcoulomb. When the capacitor is fully charged, and after a certain time, the charge on the capacitor will be decreased to 0.5 microcoulomb. So, but at what time we will reach that charge on the capacitor? This is asked. And what is the current at this time? So it is current is also asked. So how to solve this one? Again, we will use that formula, but for discharging now, okay, we have different formulas for the Q, for the discharging and charging cases, but the current is always same, the same expression, okay? If you look at that one, if you look at the current here in charging case, current in discharging case, they are same, but the charge during discharging and charge during charging, they are different from each other. So now we have expression for the charge for the discharging case, which is given by Q0 times E over minus T over RC. So RC is known from that one, 10 seconds, okay? Q0 is given here, 5 microcoulomb. Q is given 0.5 microcoulomb. Put it there, then you can calculate time, 23 seconds. After 23 seconds, the initial charge of the capacitor will be decreased to 0.5 microcoulomb, okay? It will be discharged very fast within 23 seconds. So it goes to very small value compared to the initial value of the charge. So what is the second question? What is the current at this time? So after 23 seconds, what will be the current passing through within the circuit? We have another expression here. Minus Q0 over RC. We know the Q0. Q0 is 5 microcoulomb. We know the RC. What was it? It was 10 seconds. We have already calculated. Put them here and put RC here. Put time here, 23 seconds. And then you will able to calculate the current within this circuit after 23 seconds. Okay. Then this is minus 5 times 10 to minus 8 amp. Okay, so the current in part B here is negative because I has the opposite sign when the capacitor is charging than when it is charging. We have already discussed all these things. Okay, just to remind you. So now let's have a look with bio application, pacemakers and capacitors. Pacemaker is kalp pili, okay. Here, you see an X-ray image which shows a pacemaker implanted in a patient with a malfunctioning sinotral node. What is sinotral node? Sinotral node, the part of the heart that generates the electrical signal to trigger heartbeats. So this heartbeats generated by the electrical signals produced by the heart, okay, produced by the sinotral node. So sometimes in some patients, this sinotral node does not working properly. There's a malfunctioning, okay? So the pacemaker here, kalp biliği in Turkish, the pacemaker circuit contains a battery, this one, a capacitor, and a computer controlled switch. Okay, battery, capacitor, computer controlled switch. To maintain regular beating once per second, the switch discharges the capacitor and sends an electrical pulse along the lead to the heart. So this is the pacemaker, this is the heart, these are the lungs, okay? So this is an electrical lead, goes to the heart. And this capacitor, to maintain regular beating once per second, the switch discharges the capacitor and it sends an electrical pulse along the lead to the heart. So this pacemaker sends pulses to the heart. The switch then flips to allow the capacitor to recharge for the next pulse. Okay, this is the working principle of pacemaker, and the schematic representation of the circuit is this one. Okay, so you see the importance of that chapter. And heart does it itself, okay? If the sinotral node is working properly in normal people, heart does this function properly, okay? Without need any pacemaker, something like this. So we have it in our body. So now let's continue with household electricity, power distribution systems. Here we have the basic idea of house wiring. Just consider your apartment, okay? So this is the power which is coming from the power company. This is the meter. I will show you the details. This is the main fuse, and it is splitted. This phase or hotline is splitted into different. This is the main fuse in your apartment, let's say, okay? Then this line goes to kitchen, this line goes to bedroom, and this line, another line can go to another room in your house, okay? So what we have here, we have alternating current, okay? And we have outlets. I will talk about what is outlet. And we have switch and lights, okay? So this red one is hot line. You can also consider phase. And this blue line is neutral line, okay? So what you see here, lights, you can also put another light here. They are connected in parallel, and outlets are also connected in parallel. So each device, each instrument here gets same voltage since they are connected in parallel, okay? This is the case in house wiring. So what we have here, the hot line has an alternating sinusoidal voltage, not direct current, alternating current. The direction of the current changes by time. How many times? In Turkey, for example, 50 hertz, 50 times per second. So the hot line has an alternating sinusoidal voltage with a root mean square value of 220 volt in Turkey, and 240 volt in Europe, and 120 volt in the United States and Canada. Okay, this red line, hot line, provides that voltage, alternating voltage. The neutral line is connected to ground, which is usually an electrode driving into the earth. Okay, so you see that. So now let's go into detail what we have here. So power company, this is the Dicle Dam on Dicle River in Diyarbakır, okay? So electricity is produced here. And then here we have meter in the building, okay? So this is the meter, in Turkish sayaç, okay? This is showing us there are many meters within the building of your apartment, for example. It counts how much energy you spend. So what is the main fuse and other fuses? So this is the main fuse. So you can shut down the electricity by using that shelter here. And these are controls each line. Okay, for example, this line goes to kitchen, this line goes to bathroom, for example, this line goes to another room. Okay, so you can close and open them independently, but this closes and opens each of them together. So these are the fuses. I will go into detail a little bit. And these are the outlets. This is an outlet, okay? They are connected in parallel for each room, okay? If within the room, if you have many of them, they are also connected in parallel, okay? So this is the switch here you can use at home. And here we have light. So what is the fuse here? Main fuse, fuse. This is a kind of fuse. This is a kind of fuse, okay? There are different kinds of fuses. So here we have a glass fuse. A fuse contains a link of lead tin alloy, kurşun kalay. Okay, you can see that very thin wire here produced from lead and tin. So with a very low melting temperature, the link melts and breaks the circuit when its rated current is exceeded. If you drive more current here, okay, then due to the power dissipated within that line, then very much temperature transferred to that line, and then it melts. So then no current can pass through. So, but we have also circuit breakers. This is very common in household electricity. This type of fuses can be found in the electrical instruments, in appliance. So this is this has another type of working principle. A circuit breaker is an electromechanical device that performs the same function with that one, using an electromagnet or a bimetallic strip to trip the breaker. Tripping is that one. This normally it must be on and open. When it is tripped, it goes to zero. It shuts the electricity down. Interrupt the circuit when the current exceeds a specified value. The working principle is same. If more current than the specified one passing through the circuit, then it interrupts the circuit. Circuit breakers have the advantage they can be reset after they are tripped, while a blown fuse must be replaced. So maybe you have done it many times in your life at home. So if it is tripped, then you can reopen it, okay? But if this is broken, you have to replace it. So now let's talk about two-prong plug or three-prong plug. Two-prong plug is this one. Three-prong plug is this one or this one. But we have here we have an electric drill, okay, in Turkish matkap. So there is a circuit within the electric drill. The phase is coming from that line, and here we have a resistor. You see, sometimes this resistor or this line can be broken, okay, and this current pass through on that device, okay, and if there is no ground, then this current will pass through on yourself, okay? So this will be very dangerous for you if you have two-prong plug. But in many new devices or conventional devices, there are three-prong plugs like this. The electricity comes from that line. This is the phase or hot line. Again, something is wrong within the electric drill, and the current is transferred to the chassis of the device, okay? So if you have an additional line which goes to ground, then the current will not go on yourself, okay? So you are in safe side now if you have three-prong plugs. So in United States, there are these types of plugs, okay? Two-prong plug, three-prong plug. But in Turkey, we use these types, okay? This is two-prong plug. And here again, we have two prongs, two-prong plug. But what we have here, you can see we have a metal here. We have another metal here on that side, okay? And these are connected to the ground, like this one. Let's consider that this is the phase or hot line. This is the neutral line, and this is the ground, okay? So you can see here, we have metal here, and this metal touches this metal here. Another metal here touches here. Then you can send the current to the ground. So if you check that cable for that kind of plugs, you can see that we have brown cable and blue cable here, and here we have yellow green cable. This blue one is the neutral, and this brown one is the phase or hot line, and here we have green and yellow one with double color. This is the ground, okay? So you can see that here I have one for you. So what you see here, that there is a metal here, okay, and there is another metal here, and in UPS outlets you have to use this one. This is also connected to the ground, so they go to that line here, okay. This given by double color, green and yellow color, shows us the ground line. This is the phase line or a hot line. This is the neutral line. Okay, so now let's continue with a kitchen circuit. How much power we spend within the kitchen. And 1.8 kilowatt toaster, a 1.3 kilowatt electric frying pan, and 100 watt lamp are plugged into the same 20 amp 120 volt circuit. So we have toaster, we have frying pan, okay, electrical frying pan, and we also open the lamp of the kitchen, and we are using 3 of them, and this is the main power of the house. And this is, let's consider that this is the fuse goes to the kitchen, and it allows 120 volt, okay, and maximum current allowed by this one is 20 amp. After 20 amp, this will be off. It will be tripped. So the question is that what current is drawn by each device, and what is the resistance of each device? So current and resistance of each device is asked, and will this combination trip the circuit breaker? Here we have the circuit breaker for the kitchen, let's say. So if you use this one, and lamp together, this will be enough, or it will be tripped. Okay, this is the question. So now let's have a look at the question. You can calculate total current. Since they are connected in parallel, the total current is calculated with that expression. So how to calculate the current? Current is given by power over voltage, okay? Power of the toaster is given here. Voltage provided by the household electricity is given here. For the United States and Canada, in Turkey, you can use 220 volt, okay? So then for this one, you have 15 amp for the toaster, okay? And for the frying pan, put this one here, and voltage here, 11 amp. And for the lamp, we use 0.8 amp. So again, you can also calculate the resistance of the toaster, resistance of the frying pan, and resistance of the lamp. This is given by V square over R. So power is given by V square over R. So if you take R, you will get V square over power. Then toaster resistance is 8 ohm, resistance of that guy. Resistance of that guy is 11 ohm, and resistance of the lamp is 144 ohm. So total current through the line is the sum of the currents drawn by the 3 devices. 15 amp comes from the toaster, and 11 amp comes from the frying pan, and 0.8 amp comes from the lamp. Then in total, we have 27 amp. So what was the circuit breaker? Circuit breaker allows 20 amp, and here we have 7 amps more. Okay, what will happen? This exceeds the 20 amp rating of the line, and the circuit breaker will indeed trip. So electricity will be closed, okay, by the circuit breaker. Then the cost of operating any electrical device, any electrical appliance. So let's have a look. We buy energy from the power company. The usual unit of energy sold by the power company is kilowatt hour, in Turkish kilowatt saat, 1 kilowatt times hour, okay? So 1 kilowatt hour is given by that expression, 10 to 3 watt, and 1 hour is 3,600 seconds. And then we have joule here. What is joule? Energy, okay? We buy energy from the power company. So in Turkey, 1 kilowatt hour typically costs 35 kurush, depending on the location and quantity of energy purchased. To operate a toaster, which has 1.8 kilowatt power, if you would like to use it continuously for 1 hour, it requires 1.8 kilowatt hour of energy. And for 1 kilowatt hour, energy costs 35 kurush. And for 1 hour use of that toaster costs 63 kurush. Okay, if you don't use it, please switch it off. So don't waste the energy, don't waste the water, don't waste the time. Do you have any question? With that one, I have finished my lecture. If you have any question, let me answer. Okay, if not, I will close the session. So with that one, we have finished this chapter. Please try to solve the problems at the end of the chapter and take care of yourself. Bye-bye.